The only limit to our realization of tomorrow will be our thoughts of today. Franklin D. Roosevelt. To continue with the program, we're going to listen to Dr. Andrew Thomas' dissertation, who is going to take up the next topic, the use of ambient pressure photoelectron spectroscopy for energy and catalyst applications. The academic trajectory of Dr. Andrew Thomas is as follows. He has been a research fellow at the University of Manchester since 1999, firstly in the Department of Physics before joining the Department of Materials in 2014. His research interests lie in the surface science of metal oxides with applications ranging from biomaterials, biomolecular interactions, to solar energy materials and catalysts. Working at synchrotron facilities all over Europe, he has published over than 80 papers in peer-reviewed journals, and he has collaborated with groups from Asia, Europe, Australia, and South America. In this talk, science teacher Montserrat Lopez will act as moderator, and we leave the forum to Dr. Andrew Thomas.
Okay, thank you very much. Can you see my screen, or do you see presenter view? Can you tell me?
Yes, we do. Thank you.
Okay, that's great. Thank you. Okay, so thanks very much for inviting me to speak. Okay, my title has changed slightly, but the overall theme of photocatalysts and photovoltaic materials remains the same. Apologies, I can't give my talk in Spanish. I would have to stop after buenos dias. Okay, so I'm going to talk about some research we've been doing recently on photocatalyst model photocatalysts and some photovoltaic materials, and specifically going to talk about the surface reactions and stability of these materials. So I'm going to kick off with some acknowledgements so I don't forget at the end. So Karen, Mike, Mark and Matt and Jack Chunranka are previous students who've done some of the work here. Hadil and Jack were also postdocs. These guys look after the instruments that we use in the University of Manchester. Fahad, Tom and Suresh are current students working in this area, and Wendy Flavel is a long-time collaborator of mine who's based in the Department of Physics in Manchester. We've got funding has mainly come from EPSRC, the BP ICAM, and more recently the Sir Henry Boyce Institute, which is this new institute based in Manchester. It's a building that's just been finished and we're hoping to move into fairly soon. So I'm going to start off with a fairly simple system. So surface scientists like to look at model surfaces, and the simplest system you can find is a metal with hydrogen adsorbed on the surface to try and understand the reaction of hydrogen with surfaces. We've gone slightly more complicated. We've used an oxide, so a metal oxide, and we've added water to our hydrogen. So we've added oxygen to our hydrogen to make water. And obviously the interest in this comes from the fact that 50 years or so ago, Fujishima and Honda showed that titanium dioxide could act as a photoanode and work as a photocatalytic water splitting anode when illuminated with UV radiation. And since then, the water interaction, particularly with rutile titanium dioxide and 110 surfaces under high vacuum conditions, has been very widely studied. And it's fairly well accepted now that if you absorb water onto this surface, what happens is the water will physisorb to the surface. It will kind of skate along the surface until it finds a vacancy in these so-called bridging oxygen rows. So this is the structure of the titanium dioxide 110 surface. We have the oxygen vacancy here. When the water reaches this oxygen vacancy, it will hop into here and dissociate so that a proton of hydrogen ion will jump onto a neighboring oxygen, bridging oxygen, and then we'll have two hydroxide ions, two hydroxide species then on this surface. And the reason that anatase hadn't been so well studied was mainly due to the availability of single crystals. But over the last 20 years or so, we've been able to get hold of these single crystals. And so one of the early experiments done in these UHV type studies, so in these UHV studies, what tends to happen is you prepare your model surface, get it atomically clean. You then expose it to maybe 10 to the minus 6 millibar of water, vapor, or whatever gas you're interested in. And you leave that for anything between a few seconds to a few hours. And then you pump away the gas and then you analyze your sample. So it's a kind of post-mortem study. You measure your sample before exposure, you measure again after exposure, and you look for the differences. So this was done with an anatase crystal. And the strange thing was that although anatase is the most photocatalytically active form of titanium dioxide, water didn't seem to stick at room temperature. And the only way they could get any reaction was to cool the surface down, cool the crystal down to kind of 100 Kelvin or so, condense water ice onto the surface, and then allow the sample to warm back up to room temperature. And under those conditions, they then found that there was actually some surface hydroxide formed on this anatase surface. So this is the anatase 101 surface that I'm going to be talking about. So this is the rutile 110. So we were interested in this. So when we got our new ambient pressure XPS instrument in Manchester, I'm hoping that Claudia has given an introduction to photoelectron spectroscopy. So normally we're working in photoelectron spectroscopy in low pressures, so 10 to the minus 8 to 10 to the minus 10 millibar of pressure. But this new instrument essentially uses pumping along the lens system, which allows us to measure at much higher pressures. We still can't get to atmospheric pressure, obviously, but we can now get to pressures certainly of around 6 millibar or even up to 20 millibar and still get reasonable information. So in this study, what we wanted to do was we wanted to look at how much effect oxygen vacancies at the surface had on the water absorption on this anatase surface. And could we actually get water to absorb if we went to more realistic pressures in our system? So 6 millibar water vapor pressure here would be equivalent to about 15% relative humidity at atmospheric pressure. So we start here, this is the stoichiometric surface. So we have the 2:1 oxygen to titanium ratio. And here, this is a sputtered surface. So what we did to this one is we used a cluster ion source and we gently etched the surface of this, and this will produce oxygen vacancies at the surface. Okay. For the clean surface, we see this small additional peak here due to the presence of subsurface oxygen vacancies. So in anatase TiO2 101, it's known that the vacancies sit subsurface, and this is believed to be one of the reasons that the anatase has a higher catalytic activity, because when the reactants interact with the surface, they don't heal the defect. The defect remains there below the surface, but you can still get the charge transfer occurring. So we get this additional shoulder on this side due to these subsurface vacancies. When we expose to water, you can just about make out here a small feature appearing at about 533 electron volts, which gets bigger as we increase the water vapor pressure, and this is due to adsorbed molecular water. Okay, this peak here is due to the gas phase water, so this is the water that's just around in the cell that we're using in the system. So when we confirm this just by removing the sample, and you can still see this peak is present due to the water vapor. When we then pump away the gas, we find that the molecular water disappears. So this is telling us that these molecular water on the surface is quite weakly physisorbed, but the the water will react with the oxide surface and generate some hydroxide species at the surface. So we do see some species which are remaining present on the surface. On the etched surface, we see at the very lowest water exposure, 0.6 millibar, we don't really get much molecular water adsorbed. And we think that's because the reaction with the oxygen vacancies on the surface is so fast that they're very quickly mopped up. And again, the end result, when we pump everything away, is that we end up with some oxygen, so some hydroxide present on the surface. Okay, an increase in hydroxide. So actually, it doesn't really matter very much with anatase whether you start with a stoichiometric surface or an oxygen defect surface with surface rich in oxygen vacancies. The end result is you end up with a hydroxylated surface, but the presence in the defect surface, or the surface that's been etched, you find there is a little bit more intensity associated with these subsurface defects. So it looks like the defects actually transfer subsurface. So then we wanted to go on to something a little bit more interesting. So we wanted to try and model a catalyst, an oxide supported catalyst. So we looked at silver on this anatase TiO2 101 surface, and then we wanted to look at the reaction with water and CO. So we knew that silver and rutile had been studied previously, and we knew that silver supposedly enhances the photocatalytic properties of titanium dioxide. So on the rutile 110 studies that had been done previously, it was found that the cluster size at about 1 monolayer, so this is 1 layer of silver atoms per titanium atom, the cluster size was about 1.4 nanometer high, and the lateral diameter were about 7.5 nanometers, so quite large. And we also saw that we did get some clusters forming on the terraces, but the majority of clusters tended to form along the step edges. And this is due to the fact that silver has quite a low interaction with the rutile surface, so the atoms skate across the surface until they hit a step edge, and then they can't get up the step edge, and there are defect sites and things for it to attach to, and then subsequent silver ions then build on these clusters as well. So we wanted to see what happens on anatase. So we first started off doing some core level photo emission. We started, this is the silver 3D core level spectrum. As you can see, as we increase the silver exposure, we get an increase in intensity as you expect. The titanium 2P is interesting because we see this small shoulder. This is a zoom in of this region, okay? So we see as we increase the silver coverage, we get this additional peak appearing in the titanium 2P. And this peak is associated with the reduction of titanium from titanium 4+, which you would expect in TiO2, to titanium 3+. So it's suggesting that there's some partial charge transfer into the titanium dioxide surface. And we see that after about 20 minutes of dosing time, we hit a maximum kind of increase in this. So this suggests that this is where we form a single monolayer. Beyond this, we're just adding more silver to the surface, and we don't get any more changes in the work function, or sorry, in the charge transfer into the surface. So this was quite interesting, just from a fundamental point of view. We wanted to go on and look a bit more at the structure of what was happening. So here we looked at some STM of this surface. So this is the clean surface, this kind of threefold kind of those triangular structures that you see on this anatase 101 surface. And we found when we deposit 1 minute of silver, the timing, I should point out, is not comparable to the previous slide. So the previous slide, the source and the sample were a long way apart, so we had to evaporate for much longer to get similar coverages. So we believe this coverage here is similar to what we achieved after 20 minutes for the spectra we showed on the previous slide. So we're calling this the 1 monolayer coverage. So this low coverage, but after 1 minute, where we've got very small amounts of silver on the surface, actually, if we zoom in and we do a profile across here, you can see this jump here is the step edge. We see a cluster, silver cluster on the edge there, which we can measure. We go a bit further, we've got this other silver cluster. We're also seeing some individual silver atoms on this surface, which wasn't seen on the rutile surface. Silver atoms didn't bond to the surface. So after 1 minute, the average cluster size is about 1.2 nanometers in lateral spacing and about 0.7 nanometers high. And you can see if we count the number of clusters on terraces and steps, there's a slight preference for steps, but it's not as clear as it was for the rutile surface. After 5 minutes, we've got this situation. We've now got more preference for steps compared to the terraces. The cluster size has increased to about 2.4 nanometers, but still only 0.7 nanometers high. Okay, and then finally, after 20 minutes, it's hard to define. There are a range of cluster sizes on this image here. But now the average cluster size is about 4 nanometers. So the cluster size that forms are about half what we saw on the titanium, the rutile titanium dioxide. And so what this really told us was that the silver leads to reduction of surface titanium 4+, which suggests a stronger interaction between silver and anatase titanium dioxide than with the rutile 110 surface. There appears to be some charge transfer from the silver into the rutile, sorry, into the anatase 101 surface, which doesn't occur. The clusters form both at step edges and on terraces, so that suggests that the silver ions have, or silver atoms have a lower mobility on the anatase surface. And we wonder, therefore, whether this terrace nucleation occurs at subsurface defect sites. Unfortunately, with this STM, we weren't able to get atomic resolution, which would allow us to identify these subsurface defects and see that if this is where the clusters were growing on that surface. It has been, these subsurface defects are, it can be resolved in STM. So Uli Diebold's group from Vienna have done a lot of work on that. And the final thing is that the clusters were much smaller than those seen on rutile, so they were about half the size. So again, this is possibly due to the fact we're getting more smaller clusters forming across the terraces and eventually on the steppe edges. So that was the kind of basis for the silver dose structure, which might help us understand what's happening when we actually try and do a reaction. So the reaction we studied was the water gas shift reaction, essentially. So we wanted to look at CO and water reaction on this particular surface. Now, unfortunately, we didn't have a mass spec to determine whether we were getting these products formed. And we're assuming that the concentration of these products would be very small compared to the input. So the water gas shift reaction, as you're probably all aware, we have a carbon monoxide and water coming in, and we're converting this into CO2 and hydrogen. And we know generally in the water gas shift reaction, lower temperatures improves the yield of carbon dioxide, okay, and the kind of catalysts used are mixtures of base metals and so on and so forth. So we thought we'd look at this titanium dioxide silver surface of interest, because it is of interest as a photocatalyst, and also it's kind of a model for what's happening in car catalysts as well, where you take carbon monoxide and convert to CO2. But obviously there the substrates tend to be things like ceria or yttria, which have a much higher oxygen mobility, and they're thought to take part in the reaction. And we hope that this might give us some idea about the mechanisms involved. Is it due to adsorption on the oxide, which leads to the presence of the silver, which then causes the conversion to CO2, or is there something happening on the silver? So if we look at some oxygen 1s XPS spectra, okay, so the pale yellow peak here is the oxide substrate, so the titanium dioxide substrate. Again, we've got these this intrinsic feature and some hydroxides present on the surface and some other possibly carbon oxygen species as well. When we expose to water, we get exactly the same result as we saw on the clean titanium dioxide surface. We get the formation of hydroxides, we get maybe a little more carbon oxygen species, and we see molecular water on the surface. But we don't really see any significant changes in the oxygen 1s due to the presence of the silver. When we reduce the water pressure to a half of this, so that we go from 3 millibar of water to 1.5 millibar of water and add in 1.5 millibar of carbon monoxide, we get some additional peaks. So I should have pointed out, this is the gas phase water, this is the gas phase water here, and this is the gas phase carbon monoxide now. And we see very little difference actually in the oxygen 1s spectrum. This is our subsurface defect peaks, this is our oxide substrate. This is adsorbed molecular water, so there's slightly less of it because the pressure is lower, as you would expect. Where we think this is the hydroxides, and this is probably some carbon oxygen species. And when we pump away, we're left only with the carbon oxygen species and the hydroxides. So the oxygen didn't really tell us very much, not very exciting, but the silver was slightly more interesting. So for this was the kind of coverage we were using of silver. And this is the clean UHV measurement of the silver 3D peaks that we saw earlier. So there's nothing spectacular there. It's exactly what you'd expect. We have the peak shapes are metallic-like, they're very narrow, and the binding energies correspond to metallic silver clusters. When we let in water, again, there's very little change. So we don't see any changes in the structure of the silver 3D. There's no oxidation. So again, fairly boring, and it seems to suggest that the hydroxide that we saw forming in the previous spectra in the oxygen 1s is simply due to reaction with the titanium dioxide terraces. However, when we add in the CO, the carbon monoxide, we do see some significant changes in this silver 3D spectrum. So the first thing we see are these two red peaks. These are the spin orbit split doublet, which corresponds to the main silver 3D peaks. And we also get these two blue peaks. So the red peaks here are due to oxidation of the silver. So silver, like cobalt, are strange in that normally you expect that when you oxidize a species, you move electrons from it, then the binding energy will increase, because as you go, for example, as we saw with the titanium from 3+ to 4+, the 4+ is at a higher binding energy than the 3+ peak, due to the fact that the 4+ has one fewer electrons but the same nuclear charge, so it kind of hangs on more tightly to those electrons. But silver and cobalt behave differently, and for reasons which still aren't fully understood, the binding energy of oxidized silver, so silver plus, is at a lower binding energy than silver metal. Okay, so we can see there's some oxidation occurring of the silver, and we also see these second peaks, and we're not entirely sure what these peaks are, but we believe these may be due to the presence of silver carbonyl species forming on the surface as the carbon monoxide comes down and attaches to the silver. So this is telling us that the water seems to interact with the substrate, with the titanium dioxide substrate, but the carbon monoxide is interacting almost exclusively with the silver. When we pump away after the gas, or pump away the gas, and we look again, and then pretty much the spectrum has returned to how it was in these before we exposed the gas. Okay, so there's no real change in the silver 3. There's no permanent change, and this shows one of the things that makes near ambient pressure XPS so powerful, because if we'd have done a classic surface science experiment where we exposed these gases at very low pressures and then returned to ultra high vacuum to measure, then we wouldn't actually see any reaction. So to summarize this short section on these photocatalysts, we've looked at the exposure of silver on anatase to water carbon monoxide mixtures, and we found this led to oxidation of silver clusters. Okay, and we also saw this higher binding energy peak, which we've assumed is due to silver carbonyl species, and that assignment comes mainly from other studies which have used FTIR to look at these kind of catalyst systems. And as I said, the important thing is that the silver oxide species and the silver carbonyl species only appear at the pressures achievable with NAP-XPS, and we can't observe them in the post-mortem spectra. So, as I said, we can't go back, we can't expose and then remove and go back and try and look at this again. Okay, so that's the end of the first half of my talk. So as I say, the first half of my talk, we were looking at very highly idealized crystal structures where we could have atomically clean surfaces. We could highly control the gases and the other materials which we were depositing on these surfaces. And so we can try and understand some mechanisms without all the complexities of contamination and poisoning and all this kind of thing. In the second half of my talk, I'm going to focus now on PV materials, photovoltaic materials, rather than catalysts and photocatalysts, and specifically going to talk about this lead organohalide perovskite, which I'm sure everyone's aware of. But just a little bit of background. So, as you probably all know, this is a perovskite structure, AbO3 for an oxide perovskite, certainly. We have two cations, a large cation and a small cation. So, in this case, the organic is the large methyl ammonium cation, and lead would be the small cation, and the B cation is surrounded by, in this case, halide anions. Okay, and these halides that have been used in these perovskites for solar cells can be chlorine, bromine, iodine, or a mixture of these things. Okay, but the most efficient, or the highest efficiencies that are being obtained tend to be with the iodine, the methyl ammonium lead iodide, or MAPI material. The reason these things obviously have kicked up so much excitement and interest is because in 2009 the efficiency was 3.8%. Within 6 years the efficiency had been increased to 18%, so growing large crystals with a low defect density. And so this was a huge jump, especially when you compare it to the dye sensitized solar cells, which these things were basically a form of. So the original dye sensitized solar cells hit a maximum efficiency of about 13% in 1999, and they've been there ever since. Okay, and then last year the group in Oxford made a tandem cell with silicon which had an efficiency of 30%. So we're actually getting now into a position where we can compete with silicon or improve the efficiency compared to silicon solar cells. Obviously the big problem here, big elephant in the room with these materials, is they're not stable in water or under UV, and obviously because they have lead, if they become the perovskite dissolves, then not only do we lose the functionality of the material of the devices, we also potentially have lead leaching out into the environment. So we wanted to try and understand what are the key processes occurring when these things are exposed to water. So in this particular experiment, we prepared an atomically clean strontium titanate perovskite material, and we then grew MAPI on the surface. So we exposed our strontium titanate crystal to 2 crucibles, one containing lead chloride and one containing methyl ammonium iodide. Methyl ammonium iodide was heated to 160 degrees, the lead chloride to 400 degrees, and we evaporated them simultaneously onto this crystal for about 10 minutes. Then we turned off the lead chloride and we kept the methyl ammonium iodide going for about another 20 minutes or so. We then took the sample into the chamber and we annealed it or heated it to about 100 degrees centigrade just to get full conversion of the material to the perovskite that we wanted. So here's the XPS spectra that we got from these measurements. So the red here is the strontium substrate, strontium from the strontium titanate substrate, which was quite useful because it allowed us to calibrate the binding energies on these samples. This is the pristine material, so measured in the ultra-high vacuum environment. We see this green peak here is the lead 4F. This is its spin orbit split doublet pair. So this is the 7/2, this is the 5/2. And this is some metallic lead, which we always find. It doesn't matter how we prepare these perovskite films, whether it's in vacuum by vacuum deposition, in aerosol-assisted chemical vapor deposition, or by spin coating and using anti-solvents. This is the kind of preferred method. We always see this lead when we measure these things in metallic lead when we measure these things with XPS. What we find in this case, though, as we increase the water vapor pressure in the ambient pressure cell to 3 millibar and 6 millibar, we start to see this lead peak decrease in intensity, and the metallic lead peak starts to increase in intensity. And we also see a small shift to higher binding energy, and this is indicative of conversion to lead iodide. Remember, again, as I guess Claudia pointed out, that we're only looking at the top 1 to 10 nanometers of the sample when we're using XPS. And because we can see the silver, we can see the strontium here, actually this film must be less than 10 nanometers thick in order for us to be able to see the substrate beneath. When we pump away the gas and we measure again, we can see that actually there's a substantial decrease in the intensity of the lead. It's still shifted to form to a lead position consistent with lead iodide, and we've got more metallic lead in the thing. So this is suggesting we're getting conversion first to lead iodide, and then the lead iodide is decomposing to form lead. And this is a known reaction, the photocatalyzed reaction from lead iodide to metallic lead. It occurs in the presence of moisture and photons greater than a few electron volts. The iodine is similar. We see as we increase the water vapor pressure, the peak energy decreases, and again is consistent with formation of lead iodide, and also the intensity of the peak falls away. Carbon is not so interesting, so we've basically got some hydrocarbon contamination on here, and then we have the green peak. So the green peak, which is hydrocarbon contamination, the red peak is the methyl ammonium iodide. Sorry, the methyl ammonium in the perovskite. When we expose to water, we see a shift in weight to this hydrocarbon peak. Okay, so again, this is 3 millibars. Sorry, this is pristine MAPI, 3 millibar, 6 millibar, and again after the exposure to water. So the nitrogen 1s is the most spectacular change. So this is the nitrogen 1s for our pristine sample. We see fairly strong peak. As we expose to 3 millibars, there's not much of a change, but at 60 millibar, this peak starts to decline rapidly. And when we pump away the water, it takes maybe 3 or 4 hours for the chamber to return to ultra high vacuum, and so there's still a little bit of water vapor in that cell. So this will have been exposed to water vapor for quite some time. We see this has completely disappeared. Now 9 millibar was chosen because this is corresponding to approximately 30% relative humidity at 25 degrees centigrade. We look at some numbers, okay, then we see for the iodine lead ratio before water exposure is around 3, which is what you would expect. Remember, it's methyl ammonium lead I3. After water exposure, this value has dropped to about 2.5. The nitrogen to lead ratio for the pristine sample is about 1, and after exposure is 0. So it appears that the nitrogen is completely lost from the surface. We can also look at the composition of all the other elements in there before and after. So we've normalized this to strontium. So we see a lead to iodine ratio here of about 1 to 3, as you would expect. Here, lead to nitrogen of 1 to 1, and lead to carbon of about, lead to carbon is quite high here because we've got some contamination in the system. Just to confirm as well, because we used a lead chloride precursor, we checked the chlorine content and we found there was no chlorine either before or after water exposure. So the conversion to methyl ammonium lead iodide was complete. Afterwards, as I said, the main change is that we see a huge, complete removal of the nitrogen. Okay, the carbon content doesn't really change, which suggests that any carbon that is there is being converted from one form to another. And we see obviously a loss of the lead in the compound, lead 2, as it's converted to lead, as we saw in the previous slide, and a drop in the iodine content. So to summarize what we saw, this reaction appears to occur via this process. So we have reaction of water, or also vapor, with our methyl ammonium lead iodide. It forms a hydrocarbon. Obviously this should be in brackets with an N. It's an amorphous hydrocarbon. It's not CH2, because that would just well, it wouldn't exist. And if it was methane or ethane, it would just dissolve from the surface. We also form ammonia gas, which is lost from the surface, and hydrogen iodide gas, which is also lost from the surface. We don't know whether this process would occur if we weren't in a vacuum, but obviously being in a vacuum, it means that this, if we are forming hydrogen iodide, it's likely to evaporate at these kind of temperatures at the kind of vacuum we're using. And then we're left with lead iodide on the surface. So we find that the overall process is a decompensation by reaction with water, which results in the loss of nitrogen as ammonia, and iodine probably as HI, but we're also losing some iodine due to photocatalytic degradation of this lead iodide. So the photons coming from the X-ray source seem to also lead to formation of lead and iodine. Okay, so this is unlikely to happen in a solar cell material, but obviously it does in our XPS instrument. The problems with this is obviously the hydrated perovskite phases also increase the susceptibility to things like heat and electric fields. So electric fields can cause iodine migration in these materials because the anions are quite mobile. Again, as you probably know, when we use perovskite oxides, the reason they're chosen for things like oxygen permeation membranes and fuel cells is because the oxygen mobility in perovskites, the anion mobility in perovskites is quite high, and that's the same here. And when you apply an electric field, the iodine ions will tend to drift towards the positive electrode. Okay, so these are some of the work that, well, the first one is the one that talks about the hydrated perovskite phases. The second one is our NAP-XPS study that I've just talked about now. So I'm going to finish off in the last 15 minutes or so, just summarizing some recent work we've been trying to do to try and prevent degradation of this perovskite material. Okay, there are various approaches to this. And the other thing is that because MAPI, or these perovskites, are not only useful in solar cells, they're also potentially useful in optoelectronics. And by tuning the size of, or by tuning the size of quantum dots of these materials, by making them very small, we can potentially tune the band gap. But it's very difficult actually to grow MAPI as nanocrystals using traditional techniques. And so most of the approaches that have been used have been to use some kind of encapsulation or a template in which to grow the MAPI. There's been some work using metal organic frameworks where they grow the perovskite in the pores, and they see shifts in the emission. So we thought partly because we have an excellent biomaterials group in our department who make gels from peptides. We thought, well, why don't we try encapsulating these things with a polymer gel or a peptide gel? And as I said, because we had access to these peptide gels, we started with these. So we looked at two particular peptides, FEFK, and FEFK, FEFKK. Whoops, sorry, apologies. And the amino acid sequences are phenylalanine, glutamic acid, phenylalanine, lysine. And basically, glutamic acid has an acidic side group, lysine has a basic side group, and the phenylalanine has a hydrophobic side group, this phenyl ring. When these things are put together, essentially what happens is the phenylalanine comes together, okay, and forms this hydrophobic core. And these then organize into beta sheets, which then get entangled and form a network gel material, which can be swollen by immersion in water, just like any other gel, and then subsequently dried out. And the beta sheet formation in water is indicated by an absorption peak in FTIR at about 1630 wave numbers. So the first thing we wanted to do was to ensure that DMF would also form these beta sheets, so that when we saw this gel, we were getting a similar structure to what we'd see with water, and that's what this spectrum is. So this is an FTIR spectrum of the peptide gel swollen with dimethyl formamide, which is the solvent we usually make MAPI precursors in. Now, traditionally, or normally, you would use a mixture of DMF and DMSO for your MAPI precursor delivery. But unfortunately, DMSO completely dissolves these peptide gels, so we've not been able to use that for these. So we end up with as I say, a network gel. We swell this with a MAPI precursor in DMF. We spin coat the gel onto a substrate. We then heat it to about 100 degrees centigrade to drive off the DMF. And we know for sure that the peptide is stable below about 150 degrees C, so we end up then with some perovskite. So the second peptide here with the additional lysine is more hydrophilic. So we were interested to compare what happens between these two peptide gels. Well, the first thing we did, we started with a single peptide gel, so the one without the additional lysine. We mixed it with methyl ammonium lead iodide and also with formidimium lead iodide. So we've got here, these are the two pure MAPI with no peptide, okay? So this is pure MAPI, methyl ammonium lead iodide, and this is FAPI formidimium lead iodide with no peptide. When we add the peptide, the methyl ammonium lead iodide is fine, okay? It makes quite a nice film, but the formidimium lead iodide won't actually form the perovskite. We don't know whether this is just due to steric effects, due to the larger formidimium ion, or due to the charge effect, electrostatic effect, due to the additional charge in the formidimium ion interacting with the amine side chains in the peptide. Either way, we saw that this was not going to work, so we've given up on the formidimium for the time being, and we're concentrating on the methyl ammonium lead iodide. So we were able to make these films, these quite nice films. And we did XRD, so this is our freshly made MAPI plus peptide and MAPI. And this is after they've been exposed to water, okay, or water vapor, sorry. So we've got a high relative humidity. Essentially what we did, we put the samples in a desiccator, and below where the samples were sitting, we had a pool of water, a petri dish full of water. We left these for 82 hours. So the XRD patterns here, this is for the pure MAPI. We see have strong signals associated with the methyl ammonium lead iodide. When we mix with the peptide, we also see the methyl ammonium lead iodide, but these other structures which are due partly to the peptide gel and partly due to the substrates, the ITO substrates. We can also see these weak peaks due to the ITO substrates here. When we aged them, obviously the MAPI here, the pure MAPI has just disappeared almost completely. It's slightly yellowed because, again, we've presumably formed lead iodide. We then see, we've still got some evidence of the MAPI peaks. Oh, no, we don't. Okay, so these are all these are all lead iodide peaks now that we're seeing here, and some substrate. Okay, so the MAPI peak would be this one and this one here. So most of the methylammonium lead iodide is degraded, as you can see from the picture. With the peptide, we found that there's a kind of almost gel-like structure in the middle, and the stuff around the outside has disappeared. And what we think has happened is that the MAPI doesn't actually all go into the peptide. We have some going into the peptide and then some just sitting on top of or around the peptide. And so the stuff which is not encapsulated has degraded, but the stuff which is encapsulated has been protected from the moisture for at least 82 hours. And again, if we look at the XRD, we do start to see peaks arising here now due to the presence of lead iodide, but maybe that's due to the stuff which wasn't encapsulated. But we do still see fairly strong methylammonium lead iodide peaks, this one and this one here. Okay. Oops. Okay. So we wanted to look at the optical properties. So we've got here a range of methylammonium lead iodide perovskite mixes. So the number here, 40, means this is a 40 milligrams of peptide gel mixed with 1 milligram of perovskite precursor. So we have increasing peptide concentrations as we go up on here. And you can see in each of these cases, the width of the peaks, of the diffraction peaks, increases. And if we use the Scherer formula, we find that we're actually getting an increase. So the pure MAPI, we've got a crystal size of about 70 nanometers, but by the time we've mixed it with 100 mg per mil of peptide, we've decreased the particle size to about 27 nanometers. The UV vis isn't very convincing. Okay, you can't really tell properly where the onset is, but the photoluminescence is fairly clear. So these are photoluminescence spectra, excite with a broadband light source and then measure the light that's emitted, which will give us an indication of the band gap. So the black line here is the pure MAPI with the expected emission of around 775 nanometers. But as we add the peptide in, particularly when we get up to 100 mg per mil of peptide, we see about a 30 nanometer shift, blue shift of this, which is suggesting that perhaps we are getting some quantum confinement. We see shifts, intermediate shifts at these lower peptide loadings, and we're not entirely clear because you can see they're quite broad. It's quite a broadening on this high energy side, short wavelength side of the photoluminescence spectra. So again, this might suggest that we've got a mixture of encapsulated and non-encapsulated methylammonium lead iodide, which is giving rise to this kind of broadened peak that we observe here. So we want to look at the XPS to see whether the surfaces are indeed protected. So here, P1 at the top here is the original peptide, so the one without the additional lysine, the one at the bottom here with the additional lysine. So this is the more hydrophilic material, more hydrophilic peptide, and this is this guy here. So for the nitrogen 1s, we have the pure MAPI here, and this is with the peptide mix. So obviously we have an additional nitrogen peak here, and that's because we've got the amine in the peptide, also giving rise to a signal. When we expose to water, so this is pure MAPI, this is the lowest peptide loading, and this is the highest peptide loading. You can see that as we increase the peptide loading, the relative intensity of these two peaks stays similar to what it was before. There's an additional complication here because we don't know for sure what effects the water vapor has on this peptide, okay? Whether the water vapor actually leads to protonation of some of these amine groups, and that then leads to, firstly, that we can see there's a broadening of these peaks, and also it may be that we get shift in spectral weight from one of these peaks to the other. So when you form NH3 by protonation of this thing, you get a higher binding energy peak. So some of this intensity transfers to this particular peak. So that's something we need to do next. This is, as I say, this is fairly hot off the press, only recorded in the last couple of months. But we find that overall that the MAPI protected sample, sorry, the peptide protected sample with this peptide seems to be fairly stable. With the more hydrophilic system, we actually find the protection isn't that great. Bear in mind, however, that this is only 20 mg per mil for the maximum peptide loading in this particular example. We've also looked at the lead-4F and iodine 3D XPS. I'm not going to bore you by going through all of these spectra, but essentially they confirm what we see with the nitrogen 1s, that the high loadings of peptide give us a more stable material, and the more hydrophilic peptide has a lower stability, or the perovskite formed in the more hydrophilic peptide has a lower stability. Okay. So just to summarize this section, we found that it is possible to embed methyl ammonium lead iodide into the peptide matrix using a peptide gel precursor solution. Sorry, a peptide gel mixed with a precursor solution, and we can spin coat this. And we suggest that there's a mixture of pure MAPI and also some peptide encapsulation. So we've got some SEM images here. This is the scale bar up here. So this is the peptide present. This is the pure MAPI. We're not entirely sure what the differences are here, because often pure MAPI, or usually pure MAPI, you see as they're quite granular structures in the SEM, whereas obviously we're seeing this kind of more fibrous structure. When you add in the peptide, the whole surface becomes kind of more homogeneous. So the peptide perovskite composite appears to be more homogeneous, and maybe this is also helping lead to the improved stability of the material. So it may be that these lines we're seeing here are actually the pure MAPI, and then this more kind of flatter material is the encapsulated MAPI. So we think that the structure is something like this, that we've potentially got obviously our ITO substrate. We have the composite layer and then pure MAPI sitting on top. And one of the reasons we think that is that the degradation appears to happen at the surface. Okay, so we're seeing loss of this pure MAPI material from the surface of the composite. So the next steps here are really to determine the response, as I said, of this peptide to water, to see whether we do see any changes in the protonation of the amine groups in the peptide when it's exposed to water. And that will potentially allow us to postulate a mechanism as to how the protection occurs. Obviously, these peptides will swell in water because that's what they're used for in cell culture applications. They use water to swell the gel and then grow cells on them. And so they're not keeping water out, but it may be that they prevent the water from actually reacting with the MAPI in these materials. And we also want to investigate the use of polymer gels, and the obvious reason for that is that the polymer gels are much, much cheaper than peptides to produce if we use synthetic polymers. I'm going to finish off now talking about MAPI polymer composites. This is quite short, so I'm aware of the time. So essentially, there was a paper published in 2018 by the Oxford group led by Henry Snaith, where they essentially made a cell, actually an inverted perovskite cell, and they encapsulated the perovskite with PMMA essentially by putting a layer of PMMA on top of the perovskite material. The idea there, obviously, just to keep the water out. PMMA is quite a hydrophobic material, and you can just form a barrier. So rather than trying to improve the chemistry of something which all works very well, why not just try and keep out the moisture? So we've looked at two approaches to looking at MAPI polymer composites. The first one is essentially just to mix the MAPI with the polymethyl methacrylate, okay, in different solvents, and then spin coat onto a substrate. And the second was to basically form the perovskite layer and then add a cap of the polymethyl methacrylate, okay, in toluene or chlorobenzene. So this is these are the survey spectra that we get. So we can see for the pure MAPI, we obviously see iodine, lead, nitrogen. For the blend, where we mix the two things and then spin coat them together, again, we can see all of the peaks you would expect, the lead, so the iodine, the lead-4D, lead-4F. But for the PMMA topped sample, we don't see any of the MAPI. And that's essentially now because this PMMA topping must be more than 10 nanometers thick, or around 10 nanometers thick. So we can no longer see the perovskite below the surface. So XPS, normal XPS wasn't much use for this particular one. We did do some normal XPS of the composites. Okay, so we measure the material before and after water, and actually we find that the nitrogen doesn't change appreciably for any of the blends. Okay, so PMMA, even just being mixed with the MAPI, appears to offer some protection to the MAPI. The lead 4Fs again seem to support this. So this is the pure material, and then we add in polymethyl methacrylate mixed with toluene and polymethyl methacrylate with chlorobenzene. And again, we don't really see any significant differences between these. And after water exposure, there isn't a large change. The water exposure here, I should point out, was much shorter than the one in the previous example. This was less than 24 hours. So one of the things we want to do is to try to increase that water exposure time to see if that makes a difference. And again, the iodine 3D doesn't change appreciably with the water exposure. In order to look at the MAPI topped sample, we had to go to use our new instrument in Manchester, which is a hard X-ray photoelectron spectroscopy. So it allows us to use photon energies up to 9.5 kilovolts. And when we use this, we get much higher kinetic energy of the electrons, which means we can probe deeper into the materials. So rather than 1 to 10 nanometers, we can get now between 1 and maybe 75 nanometers probe depth. And so we can now see with this high energy, this hard X-ray source, we can now see the lead and iodine in these samples. We're also seeing deeper core levels here. And as you probably all know, XPS is quite a useful tool in calculating the thickness of a film, but actually calculating the thickness of films isn't as trivial as it might sound, because we could have a carbon oxygen, so we could have a hydrocarbon layer or polymer layer forming like this, which would give a particular signal, but we'd also get the same carbon to substrate ratio peaks if we had a much thicker layer buried as an interface, or if we had a thicker layer which was actually separated into islands. And so we need to know a little bit more about the structure of the overlayer in order to be sure that we're getting a continuous film. And XPS actually allows you to do that. So there was some work done by a group in Sweden led by Sven Tugard, which showed that if you fit the background, this can give you information about the structure of the overlayer. And in our case, we found a very good fit to both the lead 3P and the iodine 2P background here. So we're not really so much worried about the actual photoelectron peak. We're interested in what happens to the photoelectrons as they come out, because it's the scattering of these photoelectrons which gives rise to the background. And depending on the structure of the overlayer, this will cause different background shapes. And we find for these two that actually an overlayer, continuous overlayer, thin film of around 10 nanometers fits this data very well. Okay, so this is just a kind of development which I think you're going to see more and more of in XPS literature in the next few years. So just to summarize this particular short experiment, we found that MAPI forms with the PMMA present in the precursor. And the work we want to go on to look at is to subject all the samples to some harsher water exposure, so for longer times. And we also want to investigate the possibility of using this PMMA capping layer to transport samples for analysis by other techniques or by other synchrotron systems for other photoelectron spectroscopy measurements, maybe to look at the valence band. And the idea would be we can cope with PMMA and then we use an argon cluster ion source, which is a gentle etching that you can have fitted in photoelectron spectroscopy instruments. And this can then remove the PMMA and allow us to look at fresh perovskite rather than perovskite which has been exposed to atmosphere, because the degradation that occurs in this perovskite is almost instantaneous as soon as it's exposed to water vapor. We also want to go on to look at the use of switchable polymer gels. So we want to put in the perovskite in a gel which is hydrophilic, and then we use pH or temperature to switch it to a hydrophobic gel, so that we can put in the polar solvents and the polar ions of the perovskite precursor. And then once we heat it up to convert it, we then want it to become hydrophobic to keep out the water. And we've just begun some device building and testing to see whether these encapsulated perovskites actually will function in a device. And apologies that I've somewhat overrun. And thank you very much for your attention.
Thank you, Dr. Andrew. That was really interesting. We are really happy to have you here with us. And we have questions. It's mixed because it's related to the research life and related to your project. Giovanna is asking, let me see, because it moved. What are some of the main challenges for a large scale application of catalysis?
Oh, well, it depends. Catalysis and photocatalysis. One of the big problems, one of the main challenges with things like car catalysts is the use of precious metals. Okay, so car catalysts are much more expensive than people want them to be, because you've got to use things like platinum and rhodium and things like this. So although they're very widely used, they try to use the minimum material. So one of the challenges is to try and either replace those precious metals or go to even smaller quantities. Okay, and obviously these things are all earth rare as well, so we reach a point where this becomes difficult anyway. In some ways that's less of a challenge, because as we move more and more towards electric vehicles and hybrid vehicles, then we don't need to worry so much about car exhaust catalysts and things like this. On a wider scale, there are so many challenges. I couldn't possibly try to cover all of them. I mean, obviously one of the big things is poisoning. That's one of the big technological challenges. A lot of catalysts, obviously a catalyst is supposed to not change when it's performing the task it's doing, but they do start to fail over time, and that's usually due to the presence of poisons. So sulfur, for example, in a lot of these precious metal catalysts is a big problem. So looking at ways of preventing sulfur poisoning, or designing new materials, or or finding ways to improve materials that don't get poisoned by sulfur. And obviously then the kind of photocatalyst side of things, it's really about trying to find materials that are both stable and active. So for example, in the water splitting applications, there's a lot of research obviously being done there to try and produce hydrogen from water, particularly on the photoanode side. What we tend to find is things like iron oxides are extremely active, but extremely soluble, so they don't last, whereas things like titanium dioxide are extremely stable, but they're not very active because they only absorb in the ultraviolet. So these are the kind of challenges we're looking to for the future.
Thank you. We just have time for one more question.
Okay.
Hilmar is asking, thank you for the presentation, Dr. Thomas. My question is, under what conditions clusters are formed?
Okay. So again, that depends on the material. So there are different growth methods when you deposit metals onto surfaces. Sometimes you'll just they will land as atoms and they will stay where they are, and essentially what happens is the atoms then grow and you end up with a continuous film. Clusters tend to form where you only have nucleation sites on the surface. So when the original atom goes down, it moves around the surface because it has a low interaction, and then it comes to some nucleation sites, and maybe a step edge or maybe a defect on the surface, and then it becomes trapped. And so then the next atom that comes down will then also have this random walk across the surface with the low interaction, and then when it meets an atom of silver in this case, it will attach, because obviously silver will tend to bond towards itself, and this will occur. So it depends upon the free energy of the surface that you're the substrate. It depends upon the free energy of the interaction between the whatever you're putting down and the surface, and then obviously on the free energy of the actual material you're depositing. So the free energy of silver is much lower than of the interaction between silver and oxygen on the oxide surface, and also much lower actually than the titanium dioxide surface. So the silver itself has quite a low free energy.
Thank you, Dr. Andrew. We have.
That's okay.
Yeah. It's like in the metals. I mean, the mechanisms are very similar. Just we are just changing the materials.
Yeah. So we grow on a surface rather than making bulk metals. Yeah.
We have a few more questions, but I will ask you if you can share with us an email to contact you in case there's some of the working with you, or some project related.
Yeah, absolutely. Yes. Yeah.
I'm gonna read. I'm so sorry. I'm gonna read the diploma in Spanish.
That's okay. Okay.
But it's a recognition for your participation in our event. We are really pleased that you could join us.
Okay, thank you.
El Tecnológico Nacional de México, Campus Instituto Tecnológico de Morelia, otorga el presente reconocimiento al Dr. Andrew Thomas por su valiosa participación como ponente de la conferencia The Use of Ambient Pressure for Electron Spectroscopy for Energy and Catalysis Applications, enmarcado en las actividades de las 22ª Jornadas Internacionales de Ingeniería en Materiales, Congreso Multidisciplinario de las Ingenierías 2021, Morelia, Michoacán, a 28 de mayo del 2021, y en the diploma is signed by el Dr. José Luis Gil Vázquez, el director de esta institución. Thank you so much, Dr. Andrew.
Thank you for the invitation, and I hope you found it useful. Thank you.
Yeah, a lot.
Bye.